So, welcome on this ConSteel webinar. This presentation will be a general presentation of ConSteel 9th version, especially the integrated structural design procedure, which is the main unique feature of ConSteel. This is a special way of design, and all the key functionalities will be presented of this special design procedure. My name is József Szalai. I'm the Technical Director of ConSteel Solutions Limited, which is the developer company, and I will make this presentation today. So I would like to start with some slides just summarizing the basic philosophy and background of this special integrated design procedure, what we think that makes a difference compared to other software products, and that is our main unique feature in ConSteel, that we treat a different way the whole design process. So I would like to start with the phases of structural design, how the whole design process is going using a software tool. First, a modeling activity should be done when we build an engineering model with members, cross-sections, supports, connectivities, loads, load cases, combinations, etc. So this is an engineering model. We are thinking in engineering objects, and this is built first in the software. The second step is the structural analysis. In this phase, a special model, usually automatically generated, this is usually a finite element model, this is the analysis model, which is capable to calculate the responses of the built engineering model. This can be deformation, internal forces, statical analysis, reactions or buckling analysis, stability or vibration, can be elastic or plastic. So lots of different analysis types can be performed. What is very important, that this phase is purely mechanics. So based on mechanical rules and nothing to do with the national standardization standard phase, because this is the last phase, the design, when we check if the performance of our model, the response of our model is adequate or not, and this is the standard design phase. Usually this phase also has a special model in the software. We call it standard model. This can be a cross-section model or a member model or another type of models in which all the design formulations, the standard design rules can be evaluated. And these are the three main phases of the whole structural design process, and I would like to present how it is built in ConSteel. First, I would like to show the usual way, the conventional way of structural design. What I would like to focus on is that how these three activities, these three phases, are connected with the real mechanical behavior of the real structure, because that is the main point. How can we model reality, and how can we evaluate and check reality, and how far we are from reality, and how many work it is to be closer to the real mechanical behavior. So in the conventional structural design way of design, these three activities are following each other, starting with modeling, then analysis and design. Usually these three activities are separated. So first we build the model, making the modeling inputs, members, supports, loads. Then if we have a model, we perform the analysis separately. Sometimes the analysis needs special inputs, analysis inputs, like mesh parameters, finite element parameters, connection stiffnesses, including somehow considering eccentricities. And then if we have the response, then we have again a separate standard design phase when we also need design inputs, special design parameters, considering the internal restraints, the effective lengths factors, the C factors, critical values, whatever. So these are special design inputs. These three types of inputs are independent of each other. So when we define an effective length, for example, it can be completely independent of our modeling inputs. So usually the software can accept anything we type in as a design parameter. And we should consider always the real structure, the real mechanical behavior when we making the assumptions for these three types of inputs. And when we have to modify, we have to optimize our structure, then we have to consider all of these phases. And when these modifications are interacting with each other, so this can be the way of optimization. If we changing something in the modeling input, then we have to consider all the other inputs if this change, this modification in the model can have an influence, for example, for some design parameters. So we have to consider this. So this is the conventional way of design. And what is different in ConSteel that we do not follow this way. We try to follow a special way, an integrated structure design procedure in which a little bit different the workflow of these phases. So we have an extended model input in the structure modeling phase, and practically the structure analysis and standard design phases are integrated as high level as it can be. So what does it mean? We have an extended model input only, so we have to build a model. What does it mean, extended? Extended means that we have to build a little bit more accurate model, considering special effects now in the modeling phases, not in the design, not in the analysis, but in the modeling, together with all the others, with the members, supports and loads, what were modeled in the conventional way as well. So when we have this extended model input, we can make a structure analysis and an integrated standard design together, and we have to consider the real mechanical behavior only in this modeling input. So when we modify, also we have to modify only our structural model, our engineering model, and all the influences and effects are automatically considered in the integrated high-level analysis and design. And what is the key point of this design procedure? How it is existing? The key point, always the middle phase, the structural analysis. So the mechanics of our mechanical possibilities of our calculations, of our structural analysis. And we think that if we increase the level of structural analysis, so if we have more knowledge about the mechanical behavior of our structure, of our model, then we can have more freedom in the modeling phase, and we can build in more intelligence in the standard design phase. Because if we can treat more problems, more configurations in the structure analysis, then we can try out more versions in the modeling, and we can build more automatism, more intelligence in the standard design, because a lots of design parameters can be directly calculated in the structure analysis phase. And based on the extended model, so the more accurate model and the higher level analysis, no need for special design parameters in the standard design phase. And we think that this special design procedure can inspire the creativity in the modeling phase, so allows wider range of structural solutions. We can optimize many ways of our structures, considering, for example, fabrication issues or material issues or whatever we want, or architecture issues. More knowledge in the analysis obviously means an increase in reliability, because we know more accurately the behavior of our model, so the assessment can be done with more safety. And of course, if we have more automatism in the standard design phase, which can be integrated with the structure analysis, that can accelerate our design work process. So the optimum design solution can be achieved very quickly. And I would like to just in a few slides present the key functionalities of these three phases of integrated structure design procedure. And these key functionalities will be demonstrated through a simple example in ConSteel, and then maybe I can show 3D models and other examples as well. So the first, for structure modeling, the first obviously most important thing, that one physical member is always one modeling object. Even if it is a tapered member like in the picture, or a hinged member, or it is divided by point loads or point supports, the physical member is still one, so any object can be connected or placed to that member. We don't have to divide it. We have automatic load cases, combinations, load placements, eccentricity considerations. These are very, very important in ConSteel, considering the effects of eccentricities, which can be member, support, or load eccentricity. So all the objects can be placed at their exact position. This is very important, as in the picture you can see that the bracing members, the purlin members can be placed to their direct place, and the influence can be evaluated. There is a complete integration of the connection geometry with geometry identification and load import. And we have a special tool for frame corners, which are usually very dominant part of the structure model. So the second phase is structure analysis. The most important thing, that ConSteel is the first design software using the 7 degree of freedom finite element for the global structural analysis. So all types of analysis, first, second order, dynamic, buckling, is performed on using this special finite element for steel members. And of course it is available in other software products, but not for the global structural analysis. We use it from the very beginning for the whole global structure analysis. And based on this element, a complete and accurate analysis can be done for torsion and warping, for any type of cross-sectional shape. A complex second-order analysis can be done, including all effects from eccentricities or imperfections. We can directly calculate all kinds of global and partial buckling modes. We can make buckling mode-based imperfections, and not only column buckling, so lateral imperfections, but any kind of lateral torsional imperfections, lateral torsional buckling, or eccentric buckling imperfections. We can perform dynamic analysis and response spectrum analysis using this special finite element. We can do plastic hinge analysis, first, second order, or plastic buckling as well, also including any, not only the in-plane second order effect and buckling, but out of plane effects and buckling effects as well. And we have shear finite element analysis as well, also first, second order buckling, and we can consider imperfections as well, so local buckling imperfections using shell elements. And finally, in the design stage, in the design phase, there are also more specific features in ConSteel. The first point is a fully automatic cross-section check based on a special thin-walled EPS section model, which means elastic plate segment model, for all types of design checks of Eurocode for normal and fire situation. It includes the automatic classification of the section, automatic generation of the necessary effective cross-section if we have class 4 cross-sections, automatic selection of relevant and dominant design checks if it is elastic, plastic, or effective, and a fully automatic check. The second phase is the stability design. We have a multi-level stability design functionality. The first point is, which is the most important, is a fully automatic stability design based on the general method of the Eurocode Part 3. This is a relatively new method in the Eurocode, but more and more application results we have, not only in ConSteel but in other software as well and in other countries, and more studies, validations, and application results published. And I should say that we are also researcher of this method as well, so the general method, and we represent the research team of this method in the TC8 working committee of the background research of Eurocode. There is a buckling sensitivity calculation for members, showing the critical members in terms of buckling. There is special member buckling checks based on the interaction methods of Eurocode Part 3, and selected eigenvalue analysis for the accurate evaluation of effective length and lateral torsional buckling parameters of members using this member buckling checks. And additionally, there are composite beam and column design based on general solid section model. This is a complete design for composite beams and columns, and a fully integrated design of a very wide range of structural connections. So these are the key functionalities, and now I would like to present the main functions through a very simple example first, just to quickly show you how we can model and how we can do the integrated analysis and design, how can we study the real behavior of our structure, how can we study the influences of our modeling modifications, and how can we optimize our model using these functionalities. So I prepared a simple portal frame for this demonstration, composed of hot rod cross sections and fixed column base. And since in ConSteel all the objects considered in the three-dimensional spatial space, we have to consider some lateral supports as well if we would like to calculate the out-of-plane behavior as well, like the out-of-plane buckling effects directly. So I put some supports perpendicular to the plane of this frame. I prepared also the loads, just simple load cases, some dead load, some wind load, and some snow load. These are the loads: dead load, two crosswind, a dominant wind pressure and a dominant wind suction, and a longitudinal wind, and finally a total and two partial snow loads. If we have these load cases, we can generate quickly any kind of combination we would like to calculate. Now I generate only the ultimate limit states based on this first option. So we can see that according to the Eurocode, altogether we have 48 load combinations, which is quite high number for this very simple structure. Usually, unfortunately, that is the result of the automatic load combination generation, because in Eurocode there are no specific restrictions of the combinations, so everything should be combined with every type of loads, and in a complex structure that can result usually or frequently many hundreds or sometimes thousands of load combinations. If we want to reduce the number of load combinations, we can check out some things. For example, the dead load can be favorable. We can check out this if we don't want to deal with this, and we can put out from the generation some loads if we think that those are not important for the relevant checks. So if I run again the load combination generation, now we can see that the dead load only considered as unfavorable, and we have only 24 load combinations now. We accept this situation, and we have now a ready complete model. So the engineering model is ready. There are supports, members, loads. The model can be evaluated by the structural analysis. So we go to the analysis tab and open the analysis parameters dialog. We can see here what kind of calculation can be done. Basically, there are three types of analysis. The statical analysis, which can be first, second order, can be done for model portion. I will show it later, and some specific features for load cases and foundation checks, and there can be calculated influence graphs if we want to apply moving loads, for example. We can calculate buckling analysis also for the whole model or for model portion, buckling sensitivity analysis showing the critical members and the contribution to the buckling forms of all the members, and we can evaluate vibration analysis as well. Now we start with statical analysis. With the first order analysis, it is very advisable that start with the most simple analysis, which is a simple first order analysis, and we can check the results, the bending moments, the deflections, and if there is some evident mistake in our model, we don't have to calculate very complicated and long calculations like buckling or vibration, and we can repair our model. So we first run a first order analysis based on a simplified combination in which the load cases are superposed for all the combinations, all the 25 combinations. So I run the analysis. So it is ready. Here we can see the results. It is the analysis type, which is calculated now only first order. Here are the load cases, calculated load cases and load combinations. We can change to any load combination, and we can see here the result types, deformations or internal forces. This is a bending moment diagram. So this is the basic visualization of the results. We can see here the values through this graph, and we can put markers anywhere. We have tables also for the results, for the extreme values, for the selected flags values, or for all the values. So this is the basic result of this first order analysis. What we can do to see the performance of our structure for this first order analysis is run a simple cross-section check. This is already the design phase. I would like to show this first and then go to the stability design. The design phases are placed to 3 different tabs. The first tab is the global checks, second member checks, and the third is serviceability checks. The global checks are specific standard design checks for which the engineer, the user, do not have to put any specific parameters. So it can be performed globally for all the structure without any specific input, additional input. And this is the basic tool for the integrated analysis and design. If we want to follow the conventional way, we can go to the member check, which follows the single isolated member evaluation. But for this member check, we should select members or group of members, and we should give additional informations, additional design parameters, backlink lengths, C factors, whatever. Of course, in ConSteel there are several automatism how to evaluate these factors, but these are specific member factors needed for the design phase, and that's why it is placed to a different tab here. And finally, the serviceability checks are deflections, swaying, etc. So I start with the global checks. We can see that basically we have 2 types of global checks for steel design. The cross-section check, which obviously a global type, so it is fully automatic. It can be done automatically for the global structure, the complete structure for all the members, all the cross-sections. So it is a global type. We don't need to put any additional design parameters. And the second type is backlink check based on the general method of Eurocode cited here. This will be shown later. So first we evaluate for all the combination the cross-section performance, the cross-section capacity. So we run the design, and what we see is a summarizing picture about the performance of our structural model. In a colored graphic, we can see the dominant utilization of our cross-sections throughout our members. What we can see that at the if we have orange or red color, that means that we are above the adequate limit, so above 100% utilization. And we can see that here in the corner region where we have the highest bending moment, at the moment the model is not adequate, so the highest utilization at these points, we can see at these points, are above 100, 140, about 140 percentage. What else we can see here in this summarization? We can see in the table the place of the cross-section, the dominant load combination. So that means that all the design checks in the cross-sections, in all the cross-sections, are performed for all the combinations, and the dominant combination, which produces the highest utilization, automatically picked as one relevant load combination, and it can be seen here. Also, one examination type is automatically selected. This is the dominant examination type from all the others which are performed. General elastic at the moment, general elastic cross-section resistance, The pure resistance is checked, plastic interaction resistance if it is adequate, if it is suitable for the cross-section, and the conservative linear summation. So all the possible checks are performed in each cross-section of our member and for all the combinations. And in each cross-section throughout the member, one dominant load combination and one dominant examination type is selected automatically, and that is seen here. So we have these utilizations, and from all the utilizations, these are the dominant ones. And if we want to see the detailed results of any cross-section, we can call by right-click the cross-section model with the detailed result. Now I show you the end cross-section of this beam, where we have the highest utilization, this 140%, and I would like to show what it offers to you. We can see here the detailed results, and we can see in the modeling tab that from all the combination, all the cross-section loads, all the internal forces are automatically received. So we have design axial force, bending moment about major axis, and minor axis shear. And the dominant combination, which is the 14th one, is automatically checked, selected, and here in the right corner we can see in the picture what are the section forces in this dominant combination. But we can check out any other combination to see the results. This is our special cross-section model, thin wall cross-section model, what is used for the standard evaluation. In this model, the cross-section is resolved into special line segments which have special attributes, upon which we can do the automatic classification. We can see that all the flanges and the webs are automatically classified for pure compression and for pure bending as well. So we can see that this cross-section is class 1 for bending and class 2 cross-section for compression. So practically this is a plastic cross-section from the point of view of design. And if we go to the standard design resistance, we can see the detailed information about the design calculations here, starting with a summary and then seeing all the performed design checks, starting with the general elastic resistance, pure resistances, plastic interaction resistance, which is now the dominant type, and the conservative interaction resistance for these loads. So if we want to see the details, first in the plastic, what we can see that since this is a class 1 cross-section and we have compression, shear and bending, there can be interaction between these forces, section forces, and it is considered in the Eurocode. So the dominant examination type is a bending about major axis plus axial force for hot rod eye-shaped sections. And we can see the standard part applied formula, and all the notations are completely the same as in the Eurocode. It can be checked and evaluated. And there are two notes in this situation. What says that the effect of axial force and effect of shear can be neglected because they are below the limit. So practically the final utilization is equal to the pure utilization for bending moment. This is the dominant load. And if we see the pure resistances, we can see the reason for it. For compression, for pure compression, only 7% the utilization, so very low. For plastic resistance, it can be neglected. For minor axis shear, it is 22.5%, which can also neglected because below 50%, which is the limit in the Eurocode, and this is the bending about major axis practical, and this is the final utilization. But since we have more forces, that's why the plastic interaction resistance is dominant and yields the same utilization at the moment. And we can see the difference of the plastic and general elastic resistance and utilization. The elastic utilization is calculated by using the elastic stresses, stress components defined in the Eurocode in that formula, and we can see that of course the utilization is higher elastically, and here we can see the components from bending and axial force, these are normal stresses. So this is for cross-section check. We should mention that if we have a class 4 cross-section, that the automatic classification is done, and an effective cross-section based on the complex stresses, complex normal stresses, are automatically generated. So practically a new cross-section automatically created by the software, and based on this effective cross-section all the design checks are evaluated. Maybe I quickly show for this section stresses. I create a new welded cross-section which have high profile. So this is a parametric section with a higher material grade. I create this, and if I select this section I can see the classification, and we can see that for pure bending and pure compression the flanges are class 1, but the web is class 4. That's why the whole cross-section is class 4 cross-section, so we have to use the effective cross-section for the design. And if we go to the standard resistance calculation, we can see that this is the effective cross-section, this is the non-effective part due to the bending moment and the compression part, and these are now the new cross-section checks. Of course, in this case the general elastic resistance is the dominant. All the elastic stresses are evaluated on the effective cross-section, considering the eccentricity of loading because of this non-effective part, etc. And this is the final utilization. Of course, we have calculated pure resistances and conservative interaction, which is available for effective cross-section as well. And we have one more cross-section check now. The web buckling resistance is done for this very thin and slender web, because the slenderness is higher than the limit, so we have to perform this as well. So I just would like to show you these cross-section checks in ConSteel. This is automatically done for all type, all shapes, all class of cross-sections, and all the internal forces, including maybe torsional forces, warping stresses, Sumbanan stresses, whatever. Everything is included in this cross-section model, and the relevant checks are automatically evaluated. So this was about cross-section design. I forgot to mention that you can ask questions at the end of the demonstration. So when I finish everything, you can ask for any parts questions, just writing into the question box in your webinar tool. So what we can see that for pure cross sections our model is not adequate, but I would like to, before I modify and optimize our frame, I would like to go on and see the stability behavior and the stability checks also of this frame. So I go back to the analysis and I run also buckling analysis. For buckling analysis, we have to calculate directly the load combinations. The superposition cannot be done because it is a nonlinear calculation. So there is a tool in ConSteel to reduce the relevant load combinations. So if we look through the load combination, we can see that only a few of them is relevant for the design, for the cross-section design. So for each cross-section, only these few load combinations produces dominant utilization. So if I select these load combinations, all of these load combinations, right-click on it, select only these combinations for the analysis, and go back to the analysis, then we can see that a reduced number of, practically this is only 5 load combinations which are relevant now. So it is automatically selected that from this very quick cross-sectional resistance and utilization calculation, which are the most dominant load combinations, and for these load combination we can perform the more time-consuming analysis, for example buckling analysis types. So we check for these combinations the buckling analysis and the first order as well. We can see that practically just we can put a number of buckling modes which are evaluated directly in ConSteel for each selected load combination. It is 10, but it can be practically any number if we have a quite large model with many finite elements. Of course, only the first, some of the first are dominant for the point of view of behavior of our model. So I run this calculation. So for this 5 load combination, we have performed first order analysis and direct buckling analysis. The first order analysis, of course, had the same results as it was using the superposition method. But if we change now for buckling, see the buckling analysis results, we can see in each combination the different buckling modes. And what we can see that the dominant buckling mode, so the first one is in all the cases some kind of lateral torsional buckling of our beam between the lateral restraints. We can see that the cross-section is moving out from the plane and rotating, twisting as well. Even at the lateral restraint, the cross-section can twist because we haven't restrained the twist at this cross-section. So this is the basic buckling mode. In this combination we can evaluate for all the load combinations, and what more we can see in this direct buckling analysis is the elastic critical load factor, load multiplier, which means that how far we are from the elastic critical state of our model. So the design loads multiplied by 4.33, we reach the elastic critical state, which have that form. This is our buckling form at this critical state. So this is a very important information if we want to go to the automatic buckling standard check using the general method of Eurocode. And if we have an accurate model in which all the member supports are at their exact position with the exact connectivities, then this buckling calculation can be very accurate. And if we evaluate the our structure model based on these buckling forms, then our results will consider all types of possible failures, which is a very safe method for evaluating our the buckling performance of our structure model. This is a very unique feature in ConSteel, and that calculation for which we need to apply this special 7 degree of freedom finite element, considering all the torsions, all the second order effects from bending moments, warpings, complete torsion, and every kind of imperfections and eccentricities. We can see later how these modifications influence the analysis results. So this is a basic feature in ConSteel, but at the moment this is only an analytic tool, so an analysis tool which sometimes available in other software products as well. What we built on this is a fully automatic buckling check of our model. So if we have these modes, these dominant buckling modes, then we can go to the global checks and automatically can check our model not only for cross-section strength but for buckling strength as well. These are the basic settings for buckling check. First, we have to decide a model portion, which will be shown later in a three-dimensional model. Now we have to consider the elastic critical factor and ultimate resistance factor for the evaluation of the buckling slenderness, which is valid for the whole structure, and we have to choose reduction factor options as well. These are specified in the Eurocode, but for the elastic critical load factor it is specified that finite element method can be used, and for this we need the special analysis buckling, direct buckling analysis, what I have shown. And if we have this result, we can run the calculation now for all of these dominant load combinations, and what we see that these are the new utilizations of our model. Of course, there are somewhat higher utilization rates. So now the highest utilization is about 150%, and the dominant examination type is now the global stability resistance of our members. And still the dominant load combination is the load combination 14. So the same as was for cross-section check, because the highest bending moment produced, of course, the most dangerous stability loss as well, stability failure as well, because our stability failure are directly connected with this bending moment, since it is a lateral torsional buckling of our beam. And if we want to see the utilization, we can see again our section model, and what we can see that here global stability resistance is shown with all the parameters. This is the applied part of the standard. This is the critical elastic critical load factor 3.73, what is received from the analysis. This is the calculated slenderness, and all the other other notations and factors are automatically evaluated according to the Eurocode. So this is what is a very, so this is the elastic critical load factor in load combination 14. So this methodology, this completely integrated stability design is very, very efficient, and we think that very reliable and safe methodology as well. Because we can see visually what's happening with our model, what is the real behavior. We can see that if we missed something from our model, if something is in a wrong place, or which are the weakest part of our model. We can decide how to strengthen, how to optimize, how to modify further our model in order to be adequate in the structural design process. And we don't have to assess by heart any additional parameter. If our model is adequate, if our structural model is accurate enough, then the evaluation shows us the realistic behavior of our model, and the global checks shows qualitatively what is the performance of our model, what are the highest utilizations, what are the critical parts. So what we see that it is not adequate at the moment, and now I would like to quickly show you how can we optimize further, make it more realistic, how can we improve the performance of our model. I start with a modification of the restraints on the beams. We can see that at the moment these restraints are defined at the reference line. This is the default arrangement of these supports. So that means that the middle of the cross section are restrained perpendicularly, laterally of the beams. But if this frame is considered to be supported by, for example, the purlin systems or specific bracing systems which are placed rather to the top flange, then this situation is not really realistic and accurate. So we have to move the supports to the upper flange of the beams, and that is what I show you. We can move it by specifying eccentricity of the supports, which should be half of the cross-section height. And if we have specified this, we can see that all the supports have been moving to the upper flange. And we can go back to the analysis and see what is the influence of this minor modification. So I run again the analysis for these combinations, and for example in this dominant combination 14 we can see that the buckling mode is completely different as it was earlier. So now the buckling is some kind of one wave buckling of the bottom compressed flange, which is completely unrestrained at the moment, and here the very high peak bending moment produces quite large compression at the bottom flange, and it can move unrestrictedly. And what is very important, that due to this new situation, the elastic critical load factor has dropped down significantly below 2. That means that the elastic critical state is just have a load multiplier of 2, which is very close to the design loads. And if we go on to the global checks, we can see that this produced an even higher utilization rate, about 15% higher, because we have now very high slenderness in our beam, and this is what is a very important unique feature in this integrated design procedure of ConSteel, that we modify something in the model, we can evaluate in the structure analysis phase the influence, and we can see the influence qualitatively through the utilization rate if we use the automatic general method for the evaluation of the buckling resistance. So again, we can see that the difference in the position of lateral restraint makes a difference in the buckling mode and a difference in the connected elastic critical load level, and also a difference in the final check of this region based on the general method, because at the moment we will have a higher slenderness value. So again, what we can conclude, that the situation is even worse than before if we make a more realistic model. So how can we advance to improve our model? First, it is evident that we should somehow strengthen the beam at the corner region, which can be obviously done by a hunch. So I quickly model here a hunch at the corner region. How can we do this? We don't have to divide our beam or make special cross sections, but we just have to click on this hunch icon and specify the dimensions, the geometry of this hunch. If we want to make it from our beam or use the dimensions of our beams to specify the geometry of the hunch, we can use this select icon, and we select this beam, and we can see that all the values are automatically refreshed, considering the geometry of this beam automatically. So the height, the thicknesses of the plates, and the width of the flanges. So we just to specify now the length of the hunch. The height can be something like this, and all the others, maybe this is changed to 12. And the position of the hunch can be lower, symmetric, or upper. Now it is lower hunch below our beam, and now we just to select the start point of our hunch, which is here, and the direction, and we made it very quickly. So without any further manipulation, we have created a hunch here, and if we run again now the analysis, we can see that at the hunch region the necessary cross sections are automatically created, and if we go to the global checks quickly, we can see that we have somewhat lower utilization now. So we have the influence of our larger cross section here, but still it is not adequate, and we can see the detailed design of this automatically generated hunched cross-section type here. So what can we do as how can we usually improve the structural performance if the buckling is dominant, beside that increasing the cross-sectional strength by hunches or tapered members or larger cross-sections? We can do another type of improvement which aims to avoid dangerous buckling situation. At the moment we can see that this is the most dominant failure mode. So how can we avoid this situation? The usual way is somehow at some point along the beam length restraining the compressed bottom flange as well. So providing somehow restraint here can efficiently improve the buckling performance of our beam and can avoid this failure mode. So how can we do this? We can go to here, and we should provide an additional restraint at the bottom flange here. We can do it quickly, just creating a new point support here, but not on the reference line, but at the bottom flange. Okay, and we put it here and here, and we will see that is that restraint enough, or in other points I should also apply this specific additional restraint. So if I run again the analysis, we can see the new results. First of all, the buckling mode is again completely different. We can see visually the effect of our new restraint. So at this cross-section, the cross-sectional rotation and also the lateral movements are completely restrained. And this has a significant influence on the buckling mode. So we can see that this is some kind of two-wave buckling mode between these restraints, and the dominant part is placed to here, where we have significantly lower bending moment, so lower compression at the flanges, and accordingly, of course, we have a significantly higher elastic critical load factor. And if we go to the general method evaluation, we can see that finally our member is adequate. With this additional restraint, we can make the utilization just below 100%. So this is a very effective way of reducing in this model the buckling utilization by avoiding this dangerous buckling mode of our beam. So this was about this cross-section and stability design in this integrated design method of ConSteel. I wanted to show you how it is working, that we modify only our structural model by considering somehow more accurately the reality, the exact places, positions of at this moment the supports. How can we visually see the behavior of our member, for which the general method makes the utilization calculations, and how can we learn the behavior of our model, and how can we learn from this behavior that how to efficiently advance the optimization. So if we have an adequate structure, now what I would like to quickly show you further is the connection design, which is also fully integrated into this design process. So I go back to the structure member tabs, and here we have the connection design functionalities. Many types of connections we have in ConSteel, which are in groups which called joints. So for example, in a beam to column joint, we can specify many connections in each flange and each side of the web. On the flanges we can specify these type of connections. On the webs we can specify these types of connections. So very flexible modeling options for creating realistic connections. This is the same for beam splices, for beam-to-beam connections for each side of the webs, etc. And we can have gusset plate bracing connections, base plate connection trusses. So if we have a global structural model, what we have now, we can use the second option, which is geometry identification. So we have to just click on the place where we want to create a connection. First, we want to create a beam to column connection here at this node, so I click there. And we can see that it is identified automatically that two members are connecting. So this is some kind of beam to column connection. We choose this type of connection and we create. And what we see is an end plate connection here, in which all the geometrical details, the profiles of the members, column and beam, the dimensions of the hinge, the angle of the beam, so the hinge here, the dimensions, everything is coming from the global model. We don't have to specify it again, so it is automatically identified, and there is a default arrangement of bolts, end plates and weds, which further can be modified, and we can add any kind of stiffener, transverse stiffener, flange stiffener, or shear stiffener. We can define more bolt throws or whatever to make it adequate our joint. But if we have this geometry, we can go and we can see first that it is evaluated for moment and for resistance and stiffness, but at the moment it is not checked because we don't know what are the dominant connection forces for which we have to check this connection. And if we want to do this, we can use the place button here, and we can place back this connection to the global structure. We can see that there is a place joint, and we can place to here as well. What does it mean? That for the positions where in the global model there is exactly the same geometry as we have in the connection, we can place those joints there. And if I end the joint placement, then it is already evaluated for utilization. We can see that it is not adequate, and we can see the joint loading, then all the calculated load combination at both positions, P1 and P2 positions, are automatically imported. So from the two positions where we have placed this connection, the loads are automatically imported from the global analysis results. And of course we can see that from these loads, the load combination 14, again the dominant one at the second position, which is the right flange. Of course this was the dominant place for the cross-section and stability check as well, because there we have the highest bending moment. And now we can start to make it adequate. For this there are specific webinars. You can see how to advance in this connection model. We can quickly do this by seeing the dominant components, for example making some stiffeners at the bottom, or here rather at the bottom here, making a higher material for the bolts, for example material grade, and larger thickness for the end plate. And now we can see that already we are close to be adequate. At the moment column web in transverse tension, this is so we can make a stiffener here or make a new bolt throw rather to make it adequate. So there are several options to create the joint to be adequate. And if we are ready with the connection details, we can save it by OK. And now I would like to show the same for the beam splice in the middle, so it is identified here. This is the received geometry with the default arrangement for bolts, weds and plates, and we place it back in order to have the possibility for evaluation. This connection, we can see that it is also not adequate at the moment, but I would like to go on to do the base plate as well, identified as a base plate, and I choose this flexible base plate in order to show you how the stiffness can be also considered in the global analysis results. So we create this model. So this is the default arrangement. Now we have also spread foundation design as well, which will be also a separate webinar. I just would like to quickly show you how can we place it back and see the performance of this basic joint. It is also not adequate. I do not want to do more work with this connection. We have several options here as well to make it adequate, but what I would like to show you that we can see that, for example, this base plate connection is semi-rigid. That means that what was assumed at the very beginning of this model, that the base plate is fixed, is now not true, and it can be considered automatically in the global analysis as well. So we can see that we have 5 positions where we have placed connections. So first of all, at these positions, all the analysis results are imported automatically to the connection design, and we can evaluate based on these positional loads the utilization of our connection. And the second influence is that at these positions, the calculated real stiffness of our cross-section, of our connection, can be automatically transferred back to the global model, which will modify the structural behavior and, for example, directly modifies the analysis results. So, for example, if we see here the bending moment diagram, which was calculated considering no connections, so considering continuous and rigid connections everywhere and fixed column bases, we have these bending moments. So the highest bending moment at the column base is 275. This is the highest bending moment for the beam, 340, and here it's 112. And if we run again the analysis, but including the connection stiffness, then calculation and all the connection stiffness are automatically modifies the finite element model. And we can see, for example, here that we have a changed situation for the bending moment. So we have considerably lower bending moment at the base plate, so at the column base. That is because we have no more fixed column base here, fixed support, but we have a semi-rigid connection there, and since the calculated stiffness is very low, maybe it is very low compared to the fixed support, it can have only this amount of bending moment. This is also changed a little bit, and this is increased. So here significant decrease in the bending moment. Here in the middle we have significantly increased bending moment, and of course it can have an impact not only the bending moment and the deflections and the statical analysis, but also on the buckling analysis. So if we see the buckling results, we can see that we have now another dominant buckling mode, which is lateral torsional buckling at the middle of our frame, so middle of our beam, and that is exactly because we have significantly higher bending moment, which produce significantly larger compression at this region, at the upper flange. And we can see that the upper flange is buckling between the restraining points. And now this is the dominant one. And of course we can see the global check based on this model, which is a more realistic model. It is still more or less adequate. We just a little bit above the adequate utilization rate, but we can see clearly the change. And of course not only in the performance of our global model, but we can see the change in the joints as well. So if I see again the utilization and the calculations of our base plate joint, we can see that the utilization is still not adequate, but considerably lower than it was before. So this was about the complete integration of the cross-section strength design, the stability design, and the connection design in a very efficient and visual way of design method, what we call integrated design procedure. And these were the basic functions, the basic steps of this design method. And the last question is that how can we apply if we have a three-dimensional model? How can we do these functions if we have not only just few members, but we have a more complex model? And maybe I show you some of these functionalities. I prepared also a three-dimensional model. It is not a very complicated model, but it is a three-dimensional model on which we can show those specific features which cannot be shown on a simple plane frame. So it is a hole in which, beside these internal frames, which are quite the same as was before, so hinged frame members which have a hot rod cross-section, we also placed there eccentrically the Z purlin system and also eccentrically the bracing system, which are this type of tension bars. And also we have a special frame at the ends of the hose with these sidewall columns. So this is the frame, the hose system, and I already prepared the load transfer surfaces, which is very important if we want to make the modeling of loads. Now I want to make automatically the meteorological loads, and I have previously prepared a load case for the live loads, but no load placement up to now. So I have defined load transfer surfaces at the walls, at all the walls. These are special objects which can transfer the surface load to line load and directly put it to the beam or column members. And what is a little bit different in this model, as we usually done, that at the roof the selected members for which we distribute the surface loads are the purlins. So not the beams, but the purlins. This is the realistic way. So the purlins get usually the surface load through the sheeting, and the beams only through the purlins. But usually it is negligible, the effect. I just would like to show you that we can do in this manner, and how can we avoid those situations which coming from this special modeling. So these are the load transfer surface. What I have to quickly do now is just making a change in the local system of the load transfer surface, and now I can do the loading. So first I put a live load to the roof, which, let's say, yeah, this amount. This is a live load. We can see that how it is taken to the transfer surface, and we can see also the distributed loads, which distributes these loads to the purlins. We can change the distribution method from uniform to the more realistic way in which we have just half at the ends. So this is the live load, and now I would like to make the meteorological load. For meteorological load, we can have here a function which can automatically make the meteorological load cases, load placements. So I click here. First, we have to define meteorological surfaces, which can be these types from the standard walls, roofs, monopitch roof, dual pitch roof, flat roof types. So these are the standard surfaces on which we can define the meteorological loads. So these are walls, these 4 surface. We can see that there is an icon signifying that this is not only a load transfer surface, but this is also a wind surface as well. And we can define the roofs as dual pitch roof. And here we can see that not only wind surface, but this is a surface for snow load as well. And we can specify here the parameters of the loading, the velocity, pressure, internal pressure, wind friction. There are a couple of methods. There will be also a separate webinar on how to do this. I just would like to move on. If we selected these surfaces, we just have to go to the meteorological load generator here. And for 0 and 90 degree, so a cross and longitudinal wind is generated together with wind friction, and we don't generate exceptional snow, but no more snow load case. So click OK, and we can see wind load is generated successfully and snow load also. And if we want to see the loads, so this is the live load, we can see here the automatically generated load cases which are possible for the wind. So this is the crosswind, one of the crosswinds, 2. So we have altogether 10 wind load cases, 8 crosswind and 2 longitudinal wind with internal load and without. So we can see here, and for snow we have these options. And of course we can see everything, how it is distributed to our members, each the cases. So it is a very quick definition of loads. Here we have the load cases, and now we have to just create the load combinations, which is of course now again a very huge number. So we can follow the same way. First, just run a first order analysis for all the combinations, but all the members holes. It is very quick. Of course we can see all the combinations. So we have the first order results here, and then we can make a global check, but at the moment we don't want to deal with the purlin and bracing system. We want to concentrate on the main structure, and then we can define model portions, and these are very important functionalities what we have here in the model portions. If we have a spatial model, a 3-dimensional model, and if we have to analyze complex models, we can easily make any kind of model portion. We can categorize them, we can group them, so making folders of model portions and everything. And these portions, this model portion is not only a modeling tool, it is far more than a modeling tool. It can have an effect in the analysis and in the design as well. So we can see what type of portions are created here, for example for purlins, for sidewall columns, for bracings, for columns, beams, for a frame, the second frame, or for the main frames. And now I would like to use this main frame portion for which the design should be done. So the cross-section evaluation are done not for the whole model but for the main frames. I apply and calculate. And now for all the combination, all the 73 combinations, all the cross-section checks are evaluated in this model portion, and the dominant combination and the dominant evaluation type are automatically selected as it was before, and we can see here the results. We can see the same graphic, the same utilizations, and the same summary of the result with the dominant load combination and dominant examination type. And we can of course see again the detailed results, but now I want to move on to the stability design and again check those combinations now for which the utilization is higher than 50%. It's starting somewhere here, yeah. We can see that from all the combinations it will just a few of them which produce higher utilization at the cross-section which are higher than 50%. The highest utilization now 123. We can see that it is not adequate at these regions again, but we will see how to repair this model. So I select these combinations for the analysis, and now for the whole main frames I would like to see the backlink results. So I select, I see the dominant combinations. We can see that from the 73 combination which are really relevant are only five of them. And first I would like to show you the backlink analysis not for the main frame but for the whole model. So which is the main problem when we have a complex model. So I run the calculation, run the analysis, and we can study the backlink results. What we see, and what is of course what we expected, that these unrestrained Z purlins are backlink at a very, very low elastic critical load value, which is below 1. That means that it is completely not adequate. So the design loads are more than two times higher than the purely elastic limit, elastic critical limit in the Z purlins in this model. It is of course not true, because these purlins are almost completely restrained by the sheeting, at least the upper flange. So this type of buckling mode is not realistic. Then why we do this? Why we model this Z purlin? We wanted to model this Z purlin system only because of their stiffness. In order to evaluate the realistic stiffness on our members, having in mind that these are taken to the top flange eccentrically to the members, having in mind that they have some kind of stiffness, axial stiffness and lateral stiffness as well, which can have an effect on the buckling of our main frames. But we are interested in the buckling of our main frames. So how can we do this? We can perform a special buckling analysis for the model portion which are relevant to us, which are now the main frames. And if we run this calculation again, we will see that the results will be completely different. And now the dominant buckling modes are the buckling of our main frames. So we can see that, of course, the filaments, the purlins are moving because they are connected to these beams, but they are only restraining systems. So they have this calculation is not dealing with the buckling of these portions, but only the buckling of the selected portions, which are now these main frames. And if we have these results, we can see the different buckling modes in all the evaluated combinations, so in these 5 combinations. So all of them, again, some kind of lateral torsional buckling of the frames, of the beams. And we can go to the global check and see the results, again, based on the first buckling mode and in the main frames. And if I evaluate this, we can see the global stability resistance, now the dominant one. In the columns, we can see the red areas, so these are not adequate at the moment. We can see again that the dominant load combination is the 46, dominant examination is the global stability. So now how can we advance to improve our model? Of course, again, we can change the cross sections, change the dimensions of our hunch, strengthen the columns, but we have some additional tool in case of this complex model. The first one is that if we see the utilizations, for example, at this corner, what we can see that, of course, the highest utilizations are always at this node, which is the corner node where we have the highest bending moment. And this node is practically just a virtual node. So it is not existing. It is not a real point of our structure. This is just the connection node of our beam and column reference line, but this is a virtual node. What does it mean? That in this region, in this corner region, the behavior is completely different. So we will have here a connection, which may be a moment end plate connection, which with stiffeners and with every kind of additional parts. And the behavior of this connection area is completely different. It's some kind of shear panel behavior, a shear box, and the bending moment and the stability should be stopped at the end of this connection. For example, here at this where we can have stiffener, and here where we have the end plate. So we have to apply only these values. And for this, we developed this frame corner wizard, in which the frame corners, so the intersection of a column and a beam member, is automatically identified, including any type of additional elements like tapering or hunches. And if we apply this, we can see in the graphics that these are those frame corners which can have a different behavior compared to our members, and these frame corners are automatically left out from the evaluation of stability and cross-section checks. What does it mean? If we run again the analysis, we will have all the results. And if we do the global checks now for the main frames, we will see that these frame corners are left out. So the black members, black parts of our models are now left out for the calculation, for the utilization calculation, and these finite elements inside in this frame region are not relevant for the specific beam and cross-section evaluation. So specific stability and cross-section strength checks, because these areas are checked when we calculate the connections. So in this way we can reduce efficiently the utilization. What else we can do? We can use the sensitivity analysis. So if we run together with the buckling sensitivity, we can check that which are the critical members, so which are the governing members which resist dominantly those buckling form which produces those utilizations. So if we go, for example, see this situation, this is the dominant load combination, and this is the first buckling mode which was applied for the whole frame. We can see that practically the dominant members are only the beams. Of course, when we see the buckling form, sometimes it is evident which are the dominant members, but this sensitivity analysis, this is a mechanical tool to evaluate the critical member based on the buckling mode and the calculated internal energy in these buckling modes. So we can see that the dominant critical members are the beam. The columns are not really having any part, not really taking any part in these buckling modes. And all the other buckling modes can be seen. And if we have these results, so these are the critical members for other buckling modes, if we have this result, we can go to the global check and run this special buckling check based on an automatic elastic critical load factor selection, which is based on the sensitivity analysis, which means that for each member the software automatically select the most relevant buckling mode, and if for some member there are completely no buckling problem, then those members are automatically left out from the stability evaluation. And if we run the analysis again, it can improve some percentage again for the evaluation. We can see now that the structure is completely adequate, because practically in the column there are the columns are in this model are not relevant for buckling evaluation. All the buckling modes, as we saw in the sensitivity analysis, are concerned with the lateral torsional buckling of our beams. So the columns will have basically higher elastic critical load factor, which are not relevant for buckling situation. If this load factor is higher than 10, according to the Eurocode, we don't have to deal any second order effect and stability effect in the member. So in this way we can optimize, use these special functions to optimize our three-dimensional model. We can use the partial model analysis, make convenient model portions and evaluate those portions separately, using this frame corner wizard to increase the efficiency of our design and decrease the utilization at the corners, and using this automatic load elastic critical load selection to the stability design. And of course, if we have a global model, just as a last point, we can have other types of connections as well. For example, if we identify this corner region now, we can see that beside the beam to column connection, we have an additional connection here which can be incorporated in this joint object, and here we do this. Here we have this lower edge connection and create, and we can see that we can directly evaluate and design together this bracing connection with this connection, and lots of connection can be covered in this way. So if we have here a bracing connection, this can be also defined here. Here are the bracing with some default arrangement, and we can place it back, and all the forces in these tension bars are automatically included. So if we have a global model, we can place several connections, several joints back to the structure. And of course, if we have connection stiffness in specific joint types, we can include it in the global analysis in the same way as I showed you in the plane frame. So these were the basic functionalities of our integrated design procedure in ConSteel, which I wanted to show you in this general presentation. Of course, there are many other functionalities in ConSteel concerning other elements, slabs, shell elements, other design parts, fire design, earthquake design, and a lot of other modeling and analysis options. But this is what we think makes very unique procedure in ConSteel, and in the steel design this can accelerate the work of an engineer. The engineer can make safer design, see visually what is the real behavior. He can approach more the accurate behavior of the designed structure, and he can benefit from this knowledge. So this is the end of this webinar, and now I would like to see if you have questions. Just please take it to the chat field, to the message field or question field, and I wait a little bit and then read it and I answer it. Until I receive possible questions, I would like to say that if you visit our website, you can see there are lots of useful information, additional information on ConSteel. There is manuals, verification manuals on our special analysis, which is the core of all of these functionalities. So there are verified examples there. You can see the specific analysis types in verification benchmark studies. There are videos from modeling, for example, how to build a model, and previous webinars. All the webinars can be seen. And as an introduction discount, we introduced ConSteel 9 recently, and we have an option to give 20% discount for users ordering until the end of April, the ConSteel 9th version. So if you don't have question, then I thank you for your participation, and I hope it was useful for you, this presentation. We recorded the presentation. It will be available in our YouTube channel, so you can see it again if you missed some parts. And this is the end of the presentation.